1400.
Okay, so let's see what we have today. Say, actually today is the topic is very good topic and lots of applications. Last class we talked about Wiener process. That Wiener process is one of the simplest random processes that exist. The characteristic of Wiener process was that derivative of Wiener process is normal distribution between 0 and 3. And then we moved on to Markov process. Is that Markov process is kind of a stochastic process that is memoryless. Probability of something given present and past is just equal to probability of something given present. We are not counting on past. That's a memoryless characteristic that we see in Markov process. We had that in Wiener process as well, but Wiener process is always considered normal distribution. But in Markov process, distribution can be anything. Markov process is just kind of characteristic of any other stochastic processes. If one stochastic process is Markov, means it's memoryless. This is what we can characterize that. But what we want to talk today? We want to talk today more about Markov. But not just Markov process. We want to go for discrete form of Markov process. That is Markov sequence. And then move to, in Markov process, in Markov sequence, we're going to have actually discrete time. And then we're going to make the state also discrete. If we make a state discrete, that's going to change to Markov chain. Like, for example, states are discrete, like a state is like sunny, rainy, cloudy. States are discrete in this case. That's called Markov chain. And then we're going to see more application of Markov idea in any other things that we call it Markov models in general. Markov models, we're going to see hidden Markov models and Markov decision models that can be used in reinforcement learning a lot. You can see the application of that. Okay, so let's go with first random sequences. What is random sequence? What is that? Be here somewhere. Okay, we can take that here. Now we can go back to normal.
Sign.
Again. Yes. Okay. So let's see what is random sequence. Random sequence in general, anytime you consider time discrete time, that random process becomes random sequence. So in random process, we had time continuous and a state also continuous. But in discrete form, discrete time process or random sequence, we have time actually discrete time. Like we can say, okay, in like states, for example, are xk. That k is a discrete number, 1, 2, 3, 4. So xk is a random variable in different time slice. Time slice 1, time slice 2, time slice 3. This kind of actually random process called random sequence. So sequence is just, in sequence case, the time is discrete. Sequence means discrete time. For example, imagine a white noise sequence. So we know white noise, WT, actually omega t, not WT. Omega t. That's a white noise. Consider white sequence. If it's white sequence, in this case, expected value of 2 points like V of k and V of j, this is autocovariance. Autocovariance is actually Q of k delta function kj. So that's this delta function is actually this delta function is 1 or 0. If k is equal to j is 1, and if k not equal to j is 0. And I think we mentioned this last class as well when we make a random process discrete time. So this is delta function, or what we call it, Kronecker delta. Kronecker delta. Kronecker is a German mathematician. So in this example, because we have k, and this k is just discrete numbers 1, 2, 3, 4, this is not white noise anymore. This is white noise sequence. It's just sequence of time, but it's just discrete in time, not in a state. A state is still continuous. So generally speaking, in random sequences, a state is still continuous, but time is discrete. So that's something example. Let I clean this up. What else? Okay, so what is Q? The Q is like a power for this white noise. We had that before too. Power, or intensity, like variance. Oh, well, it's not writing. Power or intensity. And this is a delta function, but discrete delta function that is called Kronecker delta function that is coming from this. So this is random sequence. So random sequence is in general random process in discrete time. That's it, nothing more. But let's go to Markov sequence now. Markov sequence, easily you can make this definition more broader. Say, okay, so Markov sequence is a Markov process with discrete time, of course. So because Markov is just a property. You can put the Markov in any process. You can have a Markov, a Gaussian, for example, sequence. Markov, I don't know, any kind of sequence or sequence or even process, you just can add Markov property to that to make it Markov. So Markov is just a property. What property? Property of memoryless. Property of, for example, P of k, like xk plus 1, k plus 1. That's so. Let me use another color. P of xk plus 1 given xk minus 1, xk minus 2 to x0 is equal to P of xk plus 1 given xk. That's it. If there is this property allowed in that system or in that sequence is Markov, is memoryless. So it means you don't care about the past. Example like robotic interpretation. In this example, imagine the time. Imagine the state in k plus 1 is the state k plus velocity with some actually noise. That is white noise. So having this white noise make this Markov. But this is Markov sequence because x we don't have time here. We have discrete time. Discrete time means it's not real time. It's like k equals to 1, 2, 3 to n, for example. So this is sometimes called time slice. Time slice 1, time slice 2, time slice 3. It's not continuous time. It's a discrete time. So that's Markov sequence. Okay? So the Markov sequence is Markov process in discrete time. That's it. And instead of t, we use k. Nothing more. But what about Markov chain? Markov chain has lots of application in computer. Like state space models can come in from that, you know. In Markov chain, not just time is discrete, but state is discrete too. A state is discrete too, and limited. Like we have a couple of states, like a state 1, a state 2, a state 3. We can actually have limited number of states. For example, in the weather situation, in the weather example, for example, in weather you can have sunny weather, cloudy, and rain, for example. You have 3 limited state. And when we have, that's called Markov chain. So Markov chain is like Markov sequence with limited discrete states. Very easy. So for example, a state is S1, S2, S3, and 4. But moving from one state to another state, so for example, here we have sunny state, we have rain, and we have cloud. But we need to, if there is sunny, with some probability, stay still sunny. With some probability going to rain, with some probability going to cloud, and all of these transitions need to be actually modeled. So that's why we need another property that's called transition probability. So we have transition probability that's showing if you are in this state, how you transit, how you transfer to another state. So that's called transition probability. So transition probability is a conditional probability. Saying if you are in a state Sj, what is the probability to go a state, for example, I, from a state j to I. So for example, going from sunny, a state sunny is, for example, is 0.3, for example. If go to rain is 0. For example, 5. And if from sunny go to cloudy, need to be 0.2. Because they still are probabilities, so they need to sum up to 1. That's why if you add them together, so probability of being sunny and stay sunny is 0.3, rainy 0.5, and cloudy 0.2. If you add them together in a line, they need to be add up to 1. So you also can have here, if you are in rain, and if you are in cloud, if you are in rain, probability of staying, going from rain to sunny, for example, I don't know, from rain to sunny, 0.5. From rain to rain, 0.2. From rain to cloud, 0.3. Again, if you add them up, it's going to be 1. From cloudy to sun, 0.3, for example. Cloudy to rain, 0.6, for example. And cloudy to cloud. Yeah, I should choose something. It's not very, okay. So we are making a matrix. This matrix called actually transition matrix. P. So this matrix showing the transition matrix from each state to the other state. So Markov chain open up so many applications for us because we have also discrete states. The states are countable. You have 3 states here, so you can consider that. So let's have another example. Okay, so I need to clean up some of this. Okay. So this for me is, yes, it makes a transition matrix P. And time is discrete, state is discrete, transition describes by a matrix that we explained, and also a state diagram. I also draw a state diagram showing how this transition happening from one state to another one. Example, this is example that I mentioned, or when you have grid for robots, that's also Markov chain. Like, for example, you have a robot, but the environment is a grid environment. So when you are in this state, for example, you can go this way, or this way. Imagine you just can go like that. You can't go from, this is not allowed. Going here is not allowed. So you have, in this case, you have lots of states. How many? 20 states. From each state to the other state, there is some probability. So you can, in general, you can model the grid environment with a Markov chain. Not just that, so many other applications. Like, for example, traffic lights. Traffic light can be modeled with a Markov chain as well, because the states that the traffic light can have is limited, and going from one to the other one is also can be modeled. Any question? Any other application of Markov chain coming to your mind? Like for example, in your projects or your things. Anything with discrete state kind of can, not anything, the things that at least be Markov, memoryless, you can model it with Markov chain. There is lots of application for that. Okay. Components of Markov chain. In Markov chain, we have state of states, of course. We have transition probability of being in a state I and move to J. What? T+1 is, oh, yes, so this is the probability T+1 be J if you were in I. This means that, so this is the given this. So given this, so this is the first one. So you are in a state I, and move to a state J. So this is J. So you are in a state I and move a state J. So this is P of I going to J. Okay, because it's given. So, and also the matrix. So each add up this need to be 1. P11 plus P12 plus P1n need to be 1. Total probability theorem. Yeah, here is also mentioned that Pij. So this is I, and this is J. Okay. And what else? We also need initial distribution. So probability of being in a state 0, a state 1, a state 2, and oh, we don't have a state 0, a state 1, a state 2, and a state n. So that's also initial distribution. Normally, distribution in Markov chain can be shown with pi actually. The pi showing the distribution. So p xi is p0 is like this. For all of probability of being in each of these states at the first time can be summarized in this initial distribution. Okay, we're going to see more about this pi. So pi is a distribution for random chain. Okay, another example, Weather Markov chain, I think we had that. Oh, okay, that's a real example. So imagine we have 3 states, sunny, cloudy, and rainy, and the probability of transition probability is given. Okay, so what we want to first draw the state diagram. So a state diagram is something like that I already mentioned. S1 is sunny. Maybe I just write sunny instead. Sunny. And state 2 is cloudy. State 3 is rainy. And for this is I. Oh, this is I, and this is J. Okay, so probability of change. You are sunny. 60% you can stay sunny. At 3%. You can, sorry, the 60%, 30% you can go cloudy, 0.3, and 1% rainy. And if you are in a cloudy state, 40% sunny, 40% sunny, and 40% stay cloudy, and 20% rain. And in rain, change to sunny is 0.2, change to cloudy 0.5, and stay rainy 0.3. So this is a state diagram that we have for this matrix of transition matrix. So the add of this need to be 1. So each row, if we add them up, they need to be 1. And what else? Okay. So this is something that is similar to what we had before. Oh, I already drew that here. I don't know why I drew that again. I have this here. Any question? So that's a weather example for Markov chain. Another example is island weather. Again, weather, because weather is just minimum states, just rain, cloudy. Here is just rain and clear. That's very good island. So it's just rain and clear. Rain. Okay. Rain and clear. And never rain 2 days in a row. So it means rain to rain is 0. Okay? So it means rain to cloudy is 1. That's good. If it's clear, 70% chance to rain. So 70%. And the rest, 30%, gonna be stay clear. Okay, that's not very good island. It's mostly, however, it's just rain 1 day. It's just rain 1 day and then become clear. That's not bad. But we need to see in a long term what's gonna happen. Okay, so what is the transition matrix? Transition matrix, if you are rain and stay rain is 0, stay clear is 1. If you are clear and become rain is 0.7, clear and 0.7, and 0.3 is actually you are clear and stay clear. Okay, so we have that too. Okay. Sorry, I need to clean this to show the next part. But I want to keep this diagram. So we have that. Oh, this shouldn't come now, but yeah. Okay, so this is something happen. So when we go for long term, so let's see what's happening. Imagine we define distribution for that. We say, okay, distribution, define a state distribution. A state distribution. We call it pi. We define a state distribution pi that this state can be 2 that has probability of ST is for clear, okay, clear, and probability of R for rain, RT. Okay, maybe don't need to show T, but that's fine. So this is the state distribution because we just have 2 states, probability of being clear and probability of being rainy. We can put that there, and that's showing the state distribution. we consider that pi. But this distribution can evolve in time. So we can say probability of t plus 1 is, pi t plus 1 is pi t multiplied by transition matrix. So if you multiply transition matrix to actually a state distribution for now, we can get this state. We can get this distribution of next time, and you can go ahead and repeat it many times. So this is showing us the idea, or bringing up the idea of a steady state for probability, for Markov chain probability. Okay, so I'm gonna explain again. We define pi as a state distribution. So, this is p of t. No, that's a p. Sorry. If we multiply each state distribution by transition matrix, if we multiply with the transition matrix, you're gonna get next distribution, a state distribution for the next time. So how we do that, let's see how it works. So we can say pi t plus 1 is equal to p of, it needs to be like that, p of c t plus, not plus, p of r t rain multiplied by 0, 1, 0.7, 0.3. So it means what? It means it's gonna be 0 multiply probability of being cloudy plus probability at 70%, 0.7 multiply probability of being rainy in time t. I write that like t, and it has a transpose here. So and this one multiply p of being cloudy plus 0.3 p of rainy. So it means the next time the probability is gonna be like that. And if we go ahead like a long term, we gonna have finally p is equal to p. This is for like a steady state behavior. So that's a steady state behavior. So in a steady state behavior, we can have any pi is equal to previous pi p, and these pi's are equal. They need to be equal. So to find the probability of a steady state, we need to use that formula. Let's see that how we can. In this picture, you can see that when you are going to for a long run. This is for p of rain is equal to 1. This is p of rain is equal to 0, and this is p of rain is equal to half. And when we start with these probabilities and go ahead in a steady state, they're gonna feed up to a number. We can find those numbers later. So that's nothing. It just, but I can clean it up. So the result after several days, a steady rain a probability gonna say in this, we're gonna compute that, how we can compute that. And use this in as actually a steady state behavior. You can find a steady state behavior. Okay, let's find the steady state behavior. That's called long-term stationary or a steady state behavior. In long-term stationary, P pi is equal to pi, and sigma pi is equal to 1. From these two, you can use actually for the example that we talked before, the example of island. Last example, let's compute that. For last example, what we had P of actually we had rain and cloudy. Yes, yeah, we had rain and not clear and rain. So probability of rain and P of rain and P of cloudy, if you write it in this case like that, it was equal to P of R plus, not plus, P of cloudy multiplied by this matrix. And we just have two unknown in these two equations. It's two equations, two unknown. If you write that up, it's going to be 0.7 pi c and pi r plus 0.3 pi c. So pi c going to be 10 over 17, 0.5, and pi r going to be 17, I think, is 0.41. So that 0.741 from last slide came from here. Okay, so this is how we compute a steady state for Markov chain. Okay, so what that means, it means if pi 0, yeah, this is good interpretation or explanation. If the pi 0, say pi, right, P, pi 0 is 0 and 1, for example, pi 2 is equal to 0.7 and 0.3, and pi 3 is equal to 0.21, 0.79, and go all the way. Pi n, for example, n is not infinity, but long term, 0.41 and 0.58. Whatever we computed here, 58, this is 58 and 41. Okay, so this is how we compute the steady state for Markov chain. Okay, so that was Markov chain. So lots of application for Markov chain. But this is the, let's clean up this. 40%, 41% of day rain, and 41% of days is rainy, and 49% clear in the long term. But what is Markov model? Markov model is the applied version of Markov property. Lots of property, lots of good things can come from Markov property. Lots of applications. Let's see some of these applications. So any application that have Markov property, we call it Markov model. So Markov model is practical implementation of Markov property. We have different type. Visible Markov model. We call it visible because we have also hidden. That's why we have visible. Visible Markov model is when the state is observed directly, like a robot position known, for example. If you know the robot position, here, 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 for example, if you know this position and limited, that's a Markov, visible Markov model. Okay? But sometimes you need to find these positions. For example, for robot position, they are like localization problem. You need to find it. You don't know them. You need to find it. That's become hidden Markov model. When the state is not visible, it's something that you need to find, or is not visible at all. Sometimes it's not visible at all. You just see another output. You don't care about the model, but it still is hidden Markov model. That's called hidden Markov model. When the states are hidden, states not visible. Like, for example, localization. When you want to find it, and noisy measurements. We also have another amazing application that is Markov decision process. Markov decision process, adding another things in top, put another agent in top to make decision. So you can also have action and rewards. You have action and reward. So you put another agent to make decision in a model and get reward based off your action. So this is amazing interpretation of Markov model. We're going to talk about that next class more. And we're going to see application of that. Why this is important? Because when you have somebody to make decision, you can make that decision best decision. You can make that optimal decision based off the things that this Markov property makes for you guys. You can do those. We're going to see how we can model a system as a Markov decision process next class. And example, like in motion model, for example, in Kalman filter is a Markov model and is hidden Markov model. And probabilistic transition models like a SLAM, localization is also Markov model, is still hidden Markov model. And Markov decision process is, okay, so we have transition with no control over outcome. The process just evolved by itself. I mean, we can put an agent in top. That agent makes decision, for example. However, the agent, I mean, the code that you are writing for that. And Markov decision process is active. So when we are saying is active, means we have agent. So the agent chooses actions. With actions, the action that maximize reward and minimize cost. That's why we have reward in this model. We need reward. It's not just transition matrix and a state. We also have rewards. If we go from one to another, how much we get reward. Reward is like cost, you know. You want to maximize reward, you want to minimize cost. Same. One, we need that because we want to optimize it. We want to get inference. We want to actually find the best outcome, whatever we want. It depends on the project or a model. So each transition gives a reward. Defines defining a goal or utility. And we want to find like highest utility. So we have probability of this comma supposed to be here. So S prime given last state and actions. We have action here, last state, and reward is based off being in a state and moving action and moving to the new state, how much we get reward. So this is how we model it. So we have one transition probability and one reward. So we need to define these two, and with these two we can model Markov decision. For next class we're going to talk about that. Here I made a table to see the difference between Markov model and Markov decision model. In control, in Markov model is a random transition, but in Markov decision model, agents select actions and make those. Instead of those random transitions, agent make decision, and agent can make the best decision. In output, in Markov model is the next state. In Markov decision model is the next state plus reward. And what is objective? Objective is the model, the behavior of the system in Markov model. But in Markov decision process is to maximize long-term expected rewards. We want to maximize it. And example is like a weather prediction. And in Markov decision process can be like a robot navigation or game strategy, And Markov decision process is a basic of actually reinforcement learning. So the reinforcement learning is the basic of reinforcement learning coming from Markov decision process. We can see that next class. It's an amazing topic. I hope we can get something out from that. That's it. Next class, we're going to talk more about Markov decision process.